Okay, well, good morning and good afternoon, everybody, and thanks for joining our symposium entitled Furthering Our Understanding of Ordinal Processing in Both Adults and Children. So it's well known that ordinal processing is a fundamental numerical skill that plays a key role in the development of more complex arithmetic. However, questions remain regarding the specific aspects of ordinality that may be driving this relation. And further, despite growing recognition of the importance of ordinal skills in arithmetic, relatively little is known about how children come to acquire a sense of ordinality in the first place. So this symposium brings together 4 talks that aim to do 2 things. 1, further elucidate the relations between ordinal processing and arithmetic, and 2, begin to uncover some of the underlying mechanisms that support the development of this critical numerical skill. So we're going to begin with Dr. Stephan Vogel, who will present novel evidence regarding qualitative differences in the reverse distance effect and the associations with arithmetic. Next, Sabrina Finke. Is it Finke or Finke?
In German, you'd say Finke, but okay. I don't mind.
Okay, great, good to know. And she will present evidence regarding the role of both domain-specific and domain-general skills in the development of both symbolic and non-symbolic ordering abilities. I will then present data on the role of the count list in the development of different aspects of ordinality at the start of formal schooling. And Dr. Ian Lyons will conclude with a presentation on how these different aspects of ordinality contribute to persistent dyscalculia. So each of our talks will be between 10 to 12 minutes, and we'll leave some time for questions after each. And then if there's time at the end, we can have a more general discussion as well. So I'll now turn it over to Stephan to get us started.
Hi, everybody. Thanks, Jane, for the nice introduction and for organizing the symposium. I also see a lot of familiar names in the chat already, so it's great that you're all here. And I hope that we will be able to see each other in person very soon again. So I will try now to share my screen. I hope that will work. So maybe you can give me sort of a short feedback if you can see like the first full slide. Thanks, Ian. Thumbs up. That seems to look good. Yeah, so I really look forward to an exciting session, exciting talks, and also constructive discussions. Today, I will present some data and results from a paper that was actually recently published and is the outcome of a really productive collaboration with Tom Falconberry, who did a lot of the central analysis for this work, Roland Grabner and myself. And in this study, in this work, we asked the question whether quantitative and qualitative differences in 2 very well-known behavioral effects, the canonical distance effect and the reverse distance effect, exist, and whether that has sort of an impact on the relationship with arithmetic and mathematics. So as you are all probably familiar, there is an increasing interest to better understand the basic cognitive foundation of symbolic numerical abilities and their relationship with arithmetic and mathematical competencies. And the semantic of symbolic knowledge is often associated with 2 central cognitive dimensions. The first one being numerical quantity, which can be defined as the symbolic numerical knowledge about the set size of numerals, and as Jane has introduced, numerical order, the symbolic numerical knowledge about the relative rank of a numeral or the serial position of numerals within a sequence. So there are 2 tasks that are often used to investigate these dimensions, the number comparison task and the numerical order verification task. And when we analyze the behavioral data of these tasks, 2 typical and also different reaction time effects emerge: the canonical distance effect and the reverse distance effect. And as you probably all know, the canonical distance effect can be characterized by an inverse relationship between reaction time measures and the numerical distance of 2 numbers being compared. It's a well-replicated effect, and it's also assumed that this effect basically represents internal mental and quantitative representation of numerical quantities. As such, there has also been shown in the literature sort of a consistent negative correlation and relationship between the canonical distance effect and arithmetic abilities, which has also been quantified by a meta-analysis of having an effect size of 0.135 roughly. The reverse distance effect is sort of the opposite of the canonical distance effect. It emerges when participants are asked to verify the correctness of the order of number triplets. Judgments are here faster now for small distances. So inter-item distances between the numbers of 1, for example, are judged faster as ordinal correct than larger distances, for example, inter-item distances of 2 and 3. It is also sort of a consistent finding in this small literature that it exists to the reverse distance effect. So on the group level, adults show the reverse distance effect, and on the group level also children seem to show the reverse distance effect. However, the underlying mechanisms of the reverse distance effect are still unclear, and I think we will also hear a little bit in relationship to that in our symposium here. So some researchers argue that it might be related to sort of an official specific retrieval mechanisms of learned ordinal sequences. And in terms of the relationship with arithmetic, also inconsistent findings have been reported. So there are some studies that have found sort of a negative relationship between the reverse distance effect and arithmetic abilities, who have found a positive relationship between the two, and also studies that have reported no findings. And this inconsistency in the relationship between the reverse distance effect and arithmetic abilities begs for an answer why that might be the case. So one reason why we might have this inconsistency is that the ordinal verification task does not elicit sort of a pure quantitative measure of the reverse distance effect. So in other words, that maybe individual differences in strategies or other cognitive mechanisms elicit sort of qualitative differences that lead to sort of an impure reverse distance effect. In other words, that not all individuals might show evidence for a reverse distance effect. And this is the main idea of that study, to investigate whether individual differences in the reverse distance effect and in the distance effects are quantitative or qualitative, and whether this has an influence on the association with arithmetic and mathematical abilities. To answer these questions, we collected behavioral data from 450 adults. Unfortunately, we had to remove a couple of the data due to several reasons, and we ended up with a final sample of 397 adults. Most of them were students at the time of testing. The data collection happened between 2015 and 2019, and was also part of a larger investigation. So we collected a bunch of other measurements of those individuals. The participants were tested in small groups, 4 to 12 individuals. So it was sort of a group testing situation as well. And the entire session lasted about 2.5 hours, also because we had those additional measurements that are not of interest in this talk today. The participants performed the classical numerical comparison task with 2 single-digit numerals, 1 to 9. We had 40 trials with a distance of 1 and 2, and 40 trials with a distance of 5 and 6. Participants then also performed a computerized numerical order verification task with 3 single-digit numerals from 1 to 9. We had 30 trials with a distance of 1 and 30 trials with a distance of 2 and 3, and participants had to verify the correctness of order. In addition to that, we collected arithmetic abilities with a paper-pencil task of fluency. that was also split up into two categories, small problems and large problems. And within each category, participants had to solve multiplication, addition, subtraction problems within a given time frame. And the outcome measure was basically the number of correct solved items within that time limit. We also collected data from a standardized mathematics test, the short version of the MPA. In this test, participants had also 15 minutes to solve 31 problems, multiple choice and open answer questions. And this test also covered a wide range of different higher order mathematical topics, from fractions to roots and logarithms. So turning now already to the analysis and the results. In a first step, we simply tested the existence of the distance effects on the group level. Univariate ANOVA analysis and also post hoc test analysis showed the classical canonical distance effect in the numerical comparison task and the reverse distance effect in the ordinal verification task. The post hoc t-tests also showed differences across all the different distances and also in the expected directions. So smaller distances were solved faster in the number comparison task, and smaller distances were solved faster in the ordinal verification task. For our main analysis, we used a Bayesian approach that was actually developed by Half and Rudder in 2017. And this approach uses a set of 4 hierarchical Bayesian models in order to test individual differences in the data. The first model basically tests for a null model and an effect of 0. So it reflects basically a variation as a sample noise. It's a baseline model. Then the common effect model, which assumes that there is a positive effect within the data, but that individual differences are the same. So this basically questions individual differences in the effect. Then the third model is the positive effect model. So this model assumes a positive effect, but also individual differences in the effect. So this really captures the quantitative difference aspect that we want to test. And then the last model is an unconstrained model, which captures then qualitative individual differences by assuming positive and negative effects. So also capturing individuals that show no evidence for the reverse distance effect, or maybe even show evidence for the opposite of the reverse distance effect in the ordinal verification task. Turning to the results, first looking at the canonical distance effect, the analysis showed that the preferred model for the canonical distance effect of the number comparison task is the positive effect model, so indicating that the canonical distance effect is truly a quantitative measure. In other words, all the individuals of our data set showed a canonical distance effect, but to a different degree. When we look at the reverse distance effect, the constraint model is the best model explaining the data. In other words, showing evidence for a qualitative difference. And when we actually unpack with further analysis the distribution of the reverse distance effect, we actually see evidence. Sorry, there's sort of a mismatch with the percentage numbers here, that 52% of the individuals show no evidence for a distance, for a reverse distance effect, that only 43% show actually evidence for a reverse distance effect, and that 5% of that sample actually showed evidence for a canonical distance effect within the ordinal verification task. So indicating that maybe, different aspects contribute to a different qualitative difference in the canonical distance effect. Last but not least, we tested the relationship of the distance effects with arithmetic and mathematical abilities in this more complex table. I will only highlight the most important things. We first actually split our total sample into 2 subsamples. In one sample, that actually showed evidence for the reverse distance effect, and in a second sample that showed no evidence for the the reverse distance effect. And when comparing those two groups, we do find sort of a significant difference in the relationship between the reverse distance effect, the positive effect of the reverse distance effect, and all the arithmetic mathematical measurements that were included. That is also significantly higher and different from the relationship that we observe for the reverse distance effect in the no positive effect group. In comparison, the canonical distance effect was unchanged by making this manipulation and making this sub-samples. So in both samples, the canonical distance effect showed quite equal and similar associations with all the different arithmetic and mathematical measurements across the board. So summing everything up that I have shown here on the group level, we showed evidence for a canonical distance effect and for the reverse distance effect as expected. Our Bayesian model showed evidence that the canonical distance effect is sort of a quantitative measurement, which is also consistent with a model that explains individual differences as a consequence of representational differences. Individual differences in the reverse distance effect seem to be of qualitative nature as well. So this is consistent with the notion that individuals maybe use different strategies or also different mechanisms or a combination of that to solve actually the ordinal verification task. And this has an impact on the relationship with arithmetic and mathematics. And future work, I think, really needs to ensure that the dimension of interest, in this case, the reverse distance effect, really shows a quantitative distribution in terms of individual differences in order to investigate associations with arithmetic and mathematical abilities. And that's, yeah, the end of my talk. Thanks for your attention, and looking forward to your questions and to a discussion.
Great, thanks, Stephan. So I am aware that we only have 1 hour, so maybe we'll do, one question now and then move on to Sabrina, and then perhaps some questions at the end.
Absolutely.
I have a question, if I may. Thank you for that talk. That was great. The question is about how, I guess a little technically, how did you judge a participant as showing no reverse distance effect as opposed to a very small positive effect? You know, if I were to write down a model of the positive effect, it would, a hierarchical model would, you know, draw from a distribution that included 0. And so it would seem like that model could accommodate people who in fact had no effect, but it would just treat them as a very small effect. So how did you actually identify them as having no effect rather than a small one?
Yeah, well, it was also sort of an additional analysis within the Bayesian framework that Tom Falkenberry actually used. So we basically had also sort of a confidence interval that we used within each participant and every trial that each participant basically solved in order to estimate within each participant whether there is actually then evidence for basically a positive or a negative effect, if you so will, and also put a number on the size of this effect in order then to calculate associations and correlations with arithmetic and mathematical abilities. But in terms of the precise statistics and analysis, we really would have to talk with Tom Falkenberry, because he is like the math genius behind actually the Bayesian analysis of that work.
Great. So should we move on to Sabrina?
Absolutely. Thanks again.
Great. Thanks, Stephan.
Bye-bye.
Yeah, thanks a lot. I hope you can now see my screen. Yeah.
Mm-hmm. It's not in. Oh yeah. No, it's good.
No. Yeah, it always takes a while.
Yeah.
Yeah, so today I'll present you some data from a larger project done together with the University of York. So I'm at the University of Graz. And yeah, this project was led by Karin Lander and Silke Göbel. Yeah, as Stephan already pointed out, every day we process lots of numerical information, but importantly, not only the size or magnitude of numbers matters, we also frequently process their order. For instance, if you ever visit the beautiful city of Graz, it's good to know that our office is located on the second floor, which is between the first and the third floor. Ordinality is a hot topic in numerical cognition, and surely this is partly due to the fact that ordering skills are closely related to more complex mathematics such as arithmetic. As a developmental psychologist, I was particularly intrigued by the finding that this association seems to grow stronger over the first years of primary school. So this is data from a large cross-sectional study. And here you can see partial correlations taken from multiple regression analyses predicting arithmetic performance at each grade. And the different colored lines actually present different numerical predictors of arithmetic. So, and at the very beginning of primary school, ordering actually cannot predict arithmetic at all to an incremental extent. And across the years, ordinal processing really gets an increasingly important predictor. Yeah, and at the same time, when we look at the descriptives, children clearly get more efficient during this period in the ordinal processing tasks. This is exciting, and interestingly, relatively little is known about why children come to acquire proficiency in ordinal processing. Thus, in the current study, we set out to investigate the cognitive predictors of order processing across the first years of primary school. Important to note, the cognitive mechanisms may differ depending on whether we deal with non-symbolic or symbolic numbers. When individuals solve these tasks, there are some interesting phenomena to be observed. Perhaps the most striking difference between non-symbolic and symbolic ordering are the distinct response time patterns. For non-symbolic ordering, we see a classical distance effect, which we typically also observe in cardinal magnitude comparison tasks. Reaction times are decreasing as the numerical distance between the triplets increases. Now, this is interesting. Does this mean that non-symbolic ordering tasks are actually solved like a multi-stage magnitude comparison task? For example, for this triplet, an individual may first compare the pair of dots on the left side, judging that this is larger than that, and then compare the pair of dots on the right side, judging that this is larger than that. And finally, the whole triplet is judged as being in ascending order. Thus, we propose a positive association between cardinal magnitude processing and ordering skills. But for symbolic ordering, we see something different, as we also heard in the last talk. At least some individuals are particularly fast to process adjacent sequences with a distance of 1, such as 1, 2, 3. But what's special about these sequences? There have been some ideas that individuals might benefit from retrieval from the verbal counters stored in long-term memory. Participants may be faster to decide that 1, 2, 3 is in order compared to 1, 3, 5, because 1, 2, 3 is part of the verbal counting chain in memory. This is supported by recent work showing that adults were actually fastest when judging symbolic triplets at the lower end of the counting sequence. Thus, we propose a unique contribution of counting to symbolic order processing. Moreover, we also looked at the contribution of different working memory components. Working memory allows individuals to store and manipulate limited information for short periods of time, and it plays a major role for various forms of numerical processing. Importantly, working memory should not be viewed as a monolithic construct, but instead consists of specific components for processing verbal and visual spatial information. Visual spatial working memory may be involved in splitting ordered triplets into 2 sequential magnitude comparison tasks. Verbal working memory may be particularly relevant for symbolic ordering because it enables maintaining the verbal representations of a given sequence, and these representations are in turn compared to the count list stored in working memory, in long-term memory, sorry. Thus, this is an overview of our hypotheses on the cognitive predictors. And importantly, in the present study, we didn't only look at the predictors at the very beginning of primary school, but also at the determinants of developmental change. As a side note, since we employed speeded tasks, we made sure to include processing speed as a control variable. Our sample consisted of 157 children whom we saw 3 times over the course of 2 years. All the processing skills were assessed at the end of each school year. We employed a paper and pencil measure in which children were asked to solve as many items as possible within a time limit of 90 seconds. With the exception of processing speed, all predictors were assessed in grade 1. Magnitude comparison tasks were also done in a classroom setting. Counting and working memory were assessed individually. To assess counting, children recited the verbal count list with a time limit of 60 seconds. They were asked to simply count as fast and accurately as possible, starting by 1. As measures of working memory, we used the classical span tasks, digit span, and cozy block tapping, both in a forward and backward version. Here you can see the number of correctly solved items and the ordering tasks. In blue, you can see the non-symbolic version, and in purple, the symbolic version. First of all, there's a steady increase in performance across the grades. Second, children do a lot better in the symbolic than the non-symbolic version of the task. As you can see here, the association between non-symbolic and symbolic ordering increases steadily over the course of the grades. This suggests that numerical order processing may develop towards one unitary factor. We performed linear regression analyses predicting non-symbolic and symbolic ordering in grade 1. When all predictors are considered, both non-symbolic and symbolic order processing are uniquely predicted by the manipulation component of working memory, as well as performance on the non-symbolic comparison task. So, if we look at our hypotheses, we find that order judgments rely to some extent on multiple pairwise magnitude comparisons. And also, visual spatial manipulation plays a role, possibly by splitting ordered triplets into 2 sequential magnitude processing tasks. In line with our expectations, symbolic ordering is uniquely predicted by children's counting skills. This additional mechanism may also partly explain why children were consistently able to solve many more items in this task compared to the non-symbolic version. Thus, retrieval of information from the verbal count list seems to be involved in performing symbolic order processing tasks, whereas we did not find any unique contribution of verbal working memory. We also predicted developmental change in non-symbolic and symbolic order processing between grades 1 and 2. We quantified developmental change by calculating residualized change scores. As can be seen, change in both order processing tasks was significantly predicted by visual spatial manipulation, as well as symbolic comparison tasks. Unique variance in symbolic ordering was also explained by non-symbolic magnitude comparison. But note that the regression coefficient between this predictor and the outcome variable was, the regression coefficient was negative, but the zero order correlation was 0. So this points to a classical suppression effect. Suppressive variables improve prediction of the criterion by being correlated with other predictors and suppressing criterion irrelevant variance in these predictors. In other words, the significant contribution of the non-symbolic magnitude processing task to the prediction of change in symbolic order processing may be due to the fact that it enhanced the predictive value of other variables. Thus, both visual spatial working memory and cardinal magnitude processing play a continuing role in the development of ordinal processing skills. However, note that children's proficiency with symbolic numbers seems to be particularly important for developmental change. To sum up, non-symbolic and symbolic order processing rely on largely similar cognitive mechanisms. Especially magnitude processing and visual spatial working memory play a role. However, only symbolic ordering was additionally supported by retrieval from the verbal count list. Thus, it seems to engage cognitive mechanism extending beyond pairwise magnitude comparisons and working memory. So, thanks. So, are there any questions?
Yeah, let's maybe we'll do one question again and then move on. Thanks, Sabrina. That was really good. Oh, Ian has a question.
I have a question. If somebody else has a question, I'm happy to step back. But yeah, that was a really surprising finding. So really, really interesting talk, Sabrina. Thank you. Super cool data. I was just curious what you make of the negative relationship. If I'm understanding it correctly, children who had stronger, I guess, dot comparison performance in grade 1 were showing reduced growth in sort of smaller growth in symbolic ordering from grades 1 to 2. So question 1, did I get that interpretation right? And question 2, kind of what do you make of that?
Mm-hmm. Yeah, that's maybe the most surprising finding for me. Actually, I'd like to again point out that there was actually a zero order correlation of actually zero. There was no, but when only looking isolated at those two variables, non-symbolic comparison and symbolic ordering, non-symbolic magnitude processing doesn't have any impact on the development. However, together with all the other predictors, non-symbolic magnitude processing eliminates irrelevant variance from some predictor, and or qualified reasoning, based on other analyses we did to follow up on this, is that non-symbolic magnitude comparison is strongly related to the symbolic version of this task. And so it may not be the magnitude comparison aspect per se that's important for the development of symbolic ordering, but rather the familiarity or proficiency with the symbolic number system. That's what counts. Yeah. But we also put the results in a paper. We submitted to +1, and we were very happy that it was accepted today. So if you're more interested, you can look at this paper.
And congratulations, Sabrina. That's exciting.
Oh, thanks. I'm so happy.
That's really
Would that be Finke at all? Would it be?
Yes.
Awesome.
But I'm sure it's not online yet, but it will soon be.
great. All right, so I think we'll move on here, and it's my turn. So I'll share my screen. That up. Okay. I'll do the obligatory. Did that work? Check. All right. So today I'm going to be sharing some data from a study entitled Extending Ideas of Numerical Order Beyond the Count List from Kindergarten to First Grade. So this work was conducted by myself and Ian Lyons at Georgetown University, in collaboration with Daniel Ansari from Western University, as well as Samuel Zhang and Stephanie De Jesus from the Toronto District School Board. So as previously mentioned, research on the development of ordinal skills is currently quite limited. What we do know is that young children gain practice ordering symbolic numbers when first learning to count. So most young children are able to recite the count list in the correct order by the age of 2 or 3, well before they have acquired the meaning of each number word. And while the ability to recite the count list early on does not reflect a sophisticated understanding of the ordinal associations amongst numbers, it suggests that from a young age, children are committing the count list to memory. So it thus seems reasonable to hypothesize that the count list plays a key role in shaping later understanding of numerical order. However, the extent and nature of the count list's influence on ordinal processing in childhood remains unknown. On the one hand, one might expect familiarity with the count list to facilitate ordinal judgments when the series in question matches the count list. For example, young children may rapidly recognize the sequence 1, 2, 3 as being in order, as this is consistent with what they frequently hear or see while counting. However, it's unclear whether children's extensive experience with the count list facilitates or perhaps even hinders their ability to expand their notion of numerical order beyond this list to include non-adjacent ordered sequences such as 5, 7, 9. So these are sequences that are in fact in order, but do not directly match the count list. And notably, recent research with adults suggests that it's likely the latter, or that familiarity with the count list actually impedes the processing of such trials. In particular, Graz et al. Observed that when Georgetown students were forced to classify non-adjacent ordered sequences like 5, 7, 9 as not in order, their performance on these trials substantially improved. So this suggests that even highly educated adults have a strong bias to see non-countless sequences as being not in order, even when they actually are. So the authors speculated that their findings may be a vestige of an earlier developmental struggle to extend notions of numerical order beyond the count list, and there is some initial evidence to suggest that this may be the case. So in particular, Gilmore and Batchelor recently investigated the role of the verbal count list in symbolic ordering performance among 62 6 to 8-year-old children. And intriguingly, they observed that around 1/3 of their sample consistently identify non-adjacent ordered sequences as being not in order. In fact, they scored around 0% accuracy on these trials. So this suggests that the slight performance cost associated with the processing of non-adjacent ordered sequences in adulthood may stem from a fundamental misunderstanding of what constitutes numerical order in childhood. However, the full extent and nature of this bias in early childhood when children are just entering formal schooling remains to be understood. In particular, it would be useful to understand whether it is the majority of children or only a small subset that struggle to extend the notion of numerical order beyond the count list when entering formal schooling. And further, it would be helpful to know roughly when this extended understanding of numerical order begins to emerge and whether the transition is gradual or reflects the qualitative shift in children's thinking. So the overall aim of the current study was to examine in detail whether and how the count list influences young children's understanding of different kinds of numerical order, namely sequences that do and do not match the count list. So first, we investigated whether children struggle to extend notions of ordinality beyond the count list from the beginning of kindergarten to the end of first grade. And specifically, we tested whether children perform above chance on numerical order judgments that are in fact numerically in order, but that do not match the count list. And second, we investigated whether the ability to do so develops incrementally or as the product of a more abrupt qualitative shift. And this we did in 2 ways. First, by examining changes in performance distributions, and second, by examining changes in the interrelations between different types of ordinality judgments. So to address these questions, we tracked the ordering performance of 384 children across 3 time points from the beginning of kindergarten to the end of first grade. And these data were collected as part of a joint research project between the Toronto District School Board and the University of Western Ontario. And at each time point, children completed the numeracy screener, which is a paper pencil assessment of children's basic numerical skills. The screener contains 6 different numerical tasks, but only the ordering task is relevant to the current study. The analytic sample was 56% male and primarily made up of children born in Canada. The mean age at the first time point was 5.18, and around 55% of participants were in schools classified as low or medium low SES. In the ordering task, children were presented with a series of 3 numbers and asked to determine whether they were in the correct ascending order by marking either the check or the X. And there were 4 different trial types: in order adjacent trials, or those that directly match the count list; in order non-adjacent trials, or those that are in order but do not match the count list; mixed order adjacent trials; and finally mixed order non-adjacent trials. So before beginning the task, children completed 4 practice trials to ensure that they understood the instructions, and then they had 2 minutes to complete as many trials as possible. Performance was calculated using adjusted scores that correct for guessing, in which a score of 0 indicates chance performance. So turning now to our results, our first research question asked whether young children struggled to extend the notion of ordinality beyond the count list from kindergarten to the end of 1st grade. And to answer this question, we examined trial-based performance over time. So as you can see here, children performed well above chance on the majority of trial types across all 3 time points. So as a reminder, a score of 0 here indicates chance performance. However, as hypothesized, children really struggled to recognize in order non-adjacent trials, so those that are in order but do not match the count list, as being in the correct order. So in fact, children performed well below chance on these trials across all 3 time points. So this provides some of the first evidence to suggest that at the start of formal schooling, the average child's sense of what constitutes numerical order is limited to sequences that match the count list. It is also worthwhile to point out that although performance on the in order non-adjacent trials remained unchanged from the beginning of kindergarten to the end of kindergarten, there was a significant increase in average performance by the end of 1st grade. And this improvement could either be indicative of incremental change, in which the majority of children are beginning to slowly improve over time, or it could reflect a more abrupt change in which a subgroup of children shift from perceiving in order non-adjacent sequences as not in order to in order. And the latter would provide indication that extending one's sense of order beyond the count list requires a conceptual shift in children's ordinal understanding. So we next attempted to differentiate between these 2 alternatives using both qualitative and quantitative methods. So first, we examined changes in the underlying performance distributions for each trial type over time. So if the improvement on in order non-adjacent trials is indicative of incremental change, we would expect to observe a unimodal distribution of performance on this trial type at all 3 time points, with the peak or the mode increasing from time 2 to time 3. When we see average performance increase. Conversely, if the improvement is indicative of a conceptual reclassification of non-adjacent order trials from not in order to in order, we should see a bimodal distribution reflecting 2 subpopulations of children, those who get that numerical order extends beyond the count list and those who don't. And interestingly, we observed the latter. So as you can see here, performance on in order non-adjacent trials at the beginning and end of kindergarten, so those first 2 graphs, was unimodal with a peak centered around an adjusted score of approximately -5, indicating that most children in the sample fell below chance at this stage in development. However, by the end of 1st grade, so that 3rd graph, the distribution of performance on in order non-adjacent trials became bimodal, with one peak centered over an adjusted score of approximately +5 and another centered over an adjusted score of approximately -5. And notably, this bimodality was specific to in-order non-adjacent trials, as performance on the other 3 trial types followed a unimodal distribution across all 3 time points. So these data indicate that a subgroup of children shifted from perceiving in-order non-adjacent trials as not in order in kindergarten to in order by the end of 1st grade, while another subgroup remained committed to the idea that such trials do not count as being in order across all 3 time points. So these findings are consistent with the hypothesis that improvement on such trials occurs as a conceptual shift in ordinal thinking rather than through incremental improvements. To complement these qualitative analyses, we next took a quantitative approach in which we examined changes in the interrelations among trial types over time, separately for those who correctly recognized in order non-adjacent trials as in order by the end of 1st grade, and for those who continued to perceive such trials as being not in order by this time point. So I'll refer to these groups as above chance and below chance, respectively, from here on out. So if the improved performance for the above chance group is a reflection of a conceptual shift in their ordinal understanding from time 2 to time 3, we would expect performance on these trials to relate to performance on the other 3 trial types in a manner that is substantially different from those in the group for which no shift is thought to have occurred. Importantly, we would expect this difference only to emerge after the shift at time 3. And this is precisely what we observed. So as you can see in these 3 graphs, there is no difference between the above and below chance groups and the correlations between performance on the in-order non-adjacent trials and the other 3 trial types at both time 1 and time 2. So this means that at the beginning and end of kindergarten, both groups of children were approaching the in-order non-adjacent trials in the same way. However, by the 3rd time point, or at the end of 1st grade, when the conceptual shift is thought to have occurred, there are large differences between the 2 groups. So this suggests that belonging to the group of children who were able to reliably identify non-adjacent ordered trials as in order by the end of 1st grade was associated with a significant shift in the interrelations between in-order adjacent trials and all other trial types. So these results lend further support to the hypothesis that recognizing numerical order in sequences other than those that match the count list is driven by a conceptual shift in numerical ordinal understanding rather than via incremental change. So just to conclude, these findings contribute to a small body of literature that has attempted to uncover the developmental trajectory of ordinal processing. In particular, they provide some of the first evidence to suggest that over-reliance on the count list may in fact hinder the development of more advanced ordinal skills. And we see this as similar to the whole number bias in fraction learning, in which children often incorrectly select, for example, 1/4 as larger than 1/2 due to overlearned familiarity with integers. So in the case of ordering, we propose that the count list may help early acquisition of basic ordinal concepts, but over-reliance on this list may lead to an unintended inflexibility, or the idea that numerical order is the count list. So these findings have important implications for educators, as they suggest that kindergarten teachers would do well to complement rote counting activities with skip counting as a way of emphasizing both the adjacent and non-adjacent relations amongst numbers prior to the start of formal schooling. So currently, skip counting is not introduced into the TDSB math curriculum until 1st grade, which might partially explain why we observed improved performance on non-adjacent order trials by the end of 1st grade, but not across the kindergarten year. And an important future or an area for future research would be to understand the extent to which failing to extend notions of ordinality beyond the count list to include non-adjacent relations amongst numbers may have repercussions for more complex math development. So next, Ian is actually going to present some data that sheds some light on this question. And I think we're going to have to skip questions and move right along to Ian because it is 9:50. An hour really does go by very quickly. So we'll move on to Ian. And Ian, our talks are very related, so we can save questions for both of us at the end. I'm not trying to get out of questions.
Thanks, Jane. Really, really interesting stuff. Let me just share my screen really quickly. All right, everybody see that? Okay, cool. So I will also be talking about numerical ordinal processing, and here I'm going to shift the focus to dyscalculia, right, or math learning deficits, depending on how you want to talk about them and describe them. And so Jane actually said this really nicely. And so I'm going to sort of kind of start with this assumption and formulate it more as a hypothesis. And I'm going to talk about a number of different data sets that I think contribute to this, including some new data that I'll be presenting here for the first time. So this idea is that children, and as we'll see in a second, even adults, confuse a specific highly familiar sequence that we typically refer to as the count list with the broader concept of numerical order, right? So very similar to something that Jane just suggested a moment ago. There we go. So just taking a quick step back and sort of talking about, well, what do we mean by ordinality and those sorts of things. A lot of folks have kind of set this up, but I want to really set the stage for exactly what I'm meaning here by broader concept of numerical order. So, of course, you can have this notion that individual elements within a set can be ordered arbitrarily, however you'd like. And you can do that for larger and larger sets. And then, of course, we can provide verbal labels or numerical labels for the ordinal position, the first element, the second element, the fifth element, and so on. And you can, of course, do this for larger and larger sets. We can also label these sets in different ways. And these we would call ordered sets, where the individuals within each set the individuals are ordered. We can then, of course, label the sets themselves, name them with the property of cardinality, right? That is to say, how many elements are within each set. But then, really importantly, we can also order these cardinal values, right? So in this sense, we're really starting to become a little bit more abstract, where we're taking these cardinal values and then we can reorder these. And notice what's happening is that we are now essentially kind of skipping numbers, right? And think about this in the Olympics, of course, right? So somebody might score 50 and somebody else might score 48 and somebody else might, the third place might score 32. And yet we would still rank them as first, second, and third. And the point that I want to make here is that I think that this last step here is a lot harder than we may have previously realized. And I think Jane provided some pretty convincing evidence there, but I'll also talk about some other evidence along these lines. And in particular, this is what I mean by a broader concept of order, right? This ability to do this kind of last abstraction step here. And the reason why it's harder than we may have realized is because it's often confounded with this specific highly familiar sequence that we call the countless. So that's the basic idea here. As I'll very, very quickly sort of talk about some of the relevant points here that Jane mentioned. However, before I go past this slide, I did want to do a quick shout out. So she's not just Jane Hutchison, she is Dr. Jane Hutchison, recently minted PhD. So well done and congratulations, Jane. So these are the data that Jane just showed you. And I'm going to refer to them ever so slightly, just given the theoretical focus, ever so slightly differently, given the theoretical focus here. So I'm going to refer to these sequences like 1, 2, 3, 4, 5, 6 as countless sequences, because they pretty clearly match the countless. Those that are in order, but for example, skip a number, I'm going to refer to those as non-countless sequences. And then of course you have your mixed permutations thereof. Just as the same basic data, I'm just tweaking them ever so slightly in terms of how I'm referring to them. And of course, the key thing that Jane found is that in kindergarten and even into first grade, basically, they're not only just sort of struggling with this, they are just flat out. In fact, you can even argue they're doing just fine, but they're essentially saying to us adults, nay, foolish, crazy adults, like, I reject thine ordinal madness, right? Like, this is nothing but witchery. Clearly, those are not in order, right? So along these lines, Sylvia Gatta said, well, hey, if kind of the idea is that these non-countless sequences are really hard, right? Sequences like 2, 4, 6, because people think that they're not in order, then let's just let them think that these sequences aren't in order and see what happens. Or more precisely, let's change the ordinality rules. So Jane hinted at this as well. So you have kind of in blue here, the sort of classic situation, 2, 4, 6, you're supposed to say that's in order because numerically they are in order. But then we can change the rules where we say that even though numerically this is wrong, I want you to say that 2, 4, 6 is not in order. And what Sylvia found is that actually improved performance here. So this is combined RT and error rate, so higher bar means worse performance. And you can see a pretty robust effect size showing that this improved performance that generalizes to double-digit numbers as well, and even larger effect size, right? So kind of the idea here is that, yeah, and the last point is that these are adults, right? These are highly literate, highly educated adults. And so the idea here is that these vestiges of what I would suggest is a kind of developmental challenge early on, a big hurdle that kids have to clear, we're still seeing vestiges of this in these adults. Now, these adults are, of course, well above chance in all of these situations. They can understand this, but it's slowing them down. This concept is sort of still in the way, as it were. Returning to Jane's data, I then want to focus on kind of what's happening as we shift, as these kids are getting better. And Jane pointed out really nicely that what's going on here is this sort of bimortal shift. We have some kids who are kind of getting it and some kids who aren't getting it, and she delved a little more deeply into that. Here, though, I just wanted to point out that this is actually quite consistent with another data set with slightly older children, kids looking in 1st through 3rd grade, recently published by Gilmore and Batchelor. And one of the nice things that we're seeing here is, so, we're going into sort of late 1st grade here, and you see slightly more kids in the not getting it side of the equation than in the getting it side. And we're starting to see more and more kids sort of migrate over to the getting it side, suggesting that we have this sort of developmental change more as kids are getting older. They are understanding it. And of course, we know that because by the time they become adults, they get it. Or for most people, they get it. But so for whom does this challenge continue to persist, right? So who are these kids who kind of are straggling, are sort of kind of being left behind in the not getting it phase? Well, some evidence also from Kinga Morsani and colleagues suggests that these kids, those who really, really struggle with this, in fact, as we get even older, right, moving toward a mean age of around 10, moving into sort of 4th, 5th grade, sort of, those may be dyscalculics, where of course they're doing just fine on what amount to the countless trials, using the terminology, the way they set up their data here. But as we look at the non-countless trials, that's really where we see the dyscalculics struggling relative to the controls, right? The dyscalculics here in the this line. So I said this word persist. Okay, so let's talk about children for whom dyscalculia is a really big deal, right? So even as we move into older kids, right? So here is a really remarkable data set put together by Stephan Vogel, and that Jane has been delving into and analyzing as well. So here we're going to look at 12 children with what we call persistent developmental dyscalculia. That is, they were more than a standard deviation below normal on 5 consecutive standardized math aptitude tests over the course of 4 years. If ever we're going to label anybody dyscalculic, it's going to be these kids, right? This is quite persistent, and these are older, so even older than Kinga's group, moving really into middle school at this point. So these are kids who are, really starting to lag behind. See what we see here. Of course, we have they are normal. We have our age matched group. But I also wanted to point out here, since we're sort of doing some shout outs, that it is not just Stephanie Buckton anymore. It is Professor Stephanie Buckton, now a professor at the University of Calgary. So congrats, Stephanie. I'm pretty sure you're in the audience. But anyhow, so very exciting stuff for lots of folks here, for both Jane and for Steph. But so this incredible data set that Steph put together, what did we actually find? Rather, I should say, what did Jane find when she analyzed Steph's data? So here we're just plotting them out as the different trial types. We've got countless, non-countless, and so on and so forth. And if we look at our typically developing group here, we see our classic reverse distance effect, which we now could potentially imagine that that's actually some holdover from this earlier developmental challenge, but they've gotten over this challenge, right? So these are error rates, they're well above chance here, even on these, right? And so the majority of kids in our typically developing group are, yeah, it's fine. It's a little harder, but I can still do it. The dyscalculics are at chance. So they're not just lagging behind, they are just not getting it. We're moving into middle school here, right? So I would argue this is a real issue. And so kind of the idea that I want to, and just to show the effect size here is pretty robust, even though this is a small sample size. So kind of the idea here is that, not only are children and adults confusing this highly familiar sequence of numbers, the count list, with this broader concept of numerical order, the kids who really continue to struggle to sort of make this conceptual leap, these are the kids who we're also seeing are struggling, in some cases persistently struggling in other aspects of numerical thinking. Just to kind of summarize all the stuff we've got here, up until around kindergarten, we see the majority of kids are kind of quote unquote not getting it. We start to see more and more kids as we move into 1st grade, more into sort of formal schooling, even more kids as they're getting older and older. But now kids are really starting to get it, right? The majority of children, and at this point, as we move into kind of late elementary school and certainly into middle school, I would argue that if kids are continuing to not get this, that may be indicative of serious math learning issues. But of course, even in our typically developing kids, I mentioned that these are 60 adults, they're Georgetown undergrads, they're highly numerate. So even in kids who end up getting it, who become adults, we still see vestiges of this kind of earlier developmental conceptual challenge. So as I mentioned, this step I think is harder than we realize, and it may actually have really important developmental implications. And Jane really nicely mentioned that perhaps we need to add this to the list of really counterintuitive ways in which math requires us to think counterintuitively, and thus presents a pretty major developmental challenge that we need to be focusing on as researchers and as educators, frankly. Thanks so much to all the different collaborators, in particular, Sylvia, Jane, and Steph, and of course funding agencies. And most of all, thank you all for your attention. And thanks to Jane for organizing a really cool symposium. Even if you take my talk out of it, I think the other 3 talks were really excellent. Anyway, thanks.
Great. Thanks, Ian. That was really interesting. So I know we're at 10:02, but I can stay a bit longer if anyone wants to ask any questions to either Ian or myself or any of the other speakers, I can stick around for a bit. Oh, Joanne has raised her hand.
Hi, well, that was an amazing symposium. Thanks so much, guys, for, I mean, it's just really impressive research that everyone's doing. I guess the question that I have about this is, well, I have 2 questions related, but the first one is, to what extent are the results that you guys are finding that younger kids don't understand? For example, that when an adult says 2, 4, 6, and they say that that's an order, they don't understand what that means, right? They don't understand. It's like they don't have the right definition. And I wonder how much of that is related to the instructions that they're given at the beginning of the task, right? The Gaddis et al. Research is basically, if you tell adults only the adjacent ones are in order, none of the rest of them are, then they go, fine, I can do that, no problem. So can someone comment on that, on what are the instructions, and if you thought you changed the instructions in some ways, and how would that be? Would you change the pattern of results?
Yeah.
That's a good question.
Yeah,
Ian, I feel like you probably have a better answer to this. So I'll just briefly comment to say that they do perform, or the kids do practice trials before the start of each task, which includes the non-adjacent items. So if a child didn't get it on the practice item, the evaluator would have had a chance to kind of explain why it was in order, I believe. So they would have had a chance to redo that question. But Ian, I think you have a better thoughts about this.
Yeah, I mean, so it's, so they clearly understand. I think that my sense is that they understand in terms of the task, what we're asking them to do. Because we see that they're well above chance in all the other 3 conditions, right? So it's not that they're just like, I don't get it, in general, but it's I would say that it's specific to those sort of 2, 4, 6 trials, or the non-adjacent trials, So if we changed up the instructions, so for example, if we did essentially the same thing in the Sylvia study, in the Gaddis et al. Study, basically said, yeah, you can treat these as though they're not in order. Would we expect them to do better? And I think the answer is yes. I mean, you would see all those negative bars flip to positive, right? Yeah. So if we adjusted the instructions to sort of accommodate their current conceptual understanding, would their performance improve? I think probably. But I think so. I want to answer that in one way, but there's another way to answer it, which is like, can we make this a teaching exercise? And so in other words, can the instructions be used to sort of inform them to say, hey, your concept of order is perhaps incomplete. You might want to expand that. That I think probably, but that's now an intervention, not an assessment, right? And so what does the nature of that intervention look like? Because at that point, like the purpose of the interaction with the task is to change understanding as opposed to evaluate based on a particular set of task constraints, right? So you could then ask, well, okay, given these task constraints, is this actually a reasonable measure of their actual understanding, right? Their actual underlying understanding. And I would say, I don't know, but that gets into really dangerous territory where you're basically saying, well, this is the task that defines what they know, and this is the task that doesn't define what they know, and so on. So Steph has some really interesting data where she shows that if you actually get kids to sort of generate, you can get kids to generate these sequences, and they seem to be okay at that. And in fact, in certain ways, they show more canonical distance effects, which I think is pretty interesting. Yeah, and so I think that's granted, there's some issues with the task design that, not to say that's a bad task design, but that could explain why you get the canonical distance effect. Point being, the kids can do this in different contexts, which I think is interesting. And I think we need to take a step back and think about ordinal processing more broadly. However, I don't think that undermines the idea that they can't do it in this context, right? So we have this weird situation where we flipped, where basically in there are plenty of other domains where kids are able to perfectly sort of comprehend things, but when they have to produce things, they really fall down. Here we have an interesting situation where it's reversed, where they seem to be able to produce, but they are having trouble comprehending. Anyway, that's kind of my spiel there, but you seem to have a different idea, Joanne, so go for it.
Well, it is, as usual, Ian, you and I often have different ideas, but not in a bad way, only in a good way. I guess I just think that I actually kind of agree with your framework that you had at the beginning, which is that the idea of first, second, and third is a higher level concept that the kids have to learn, right? It's not learning the counting sequence 1, 2, 3, 4 is one thing, and it's memorized and they get very familiar with it. But the idea of things can be in order even when they are not numerically adjacent, that's the hard part, right? That's the piece. I just think we should be a little bit careful about not saying that they're over relying on the count list exactly, because they're sort of doing exactly what they've learned to do, right? It's just that when you change the task on them, you say, oh, well, now I mean something a little bit different by order, and you don't really understand that yet. And so you have to learn that. I think that's a slightly different interpretation, that's all. So I actually think that your initial framework actually captures it really nicely. So I'm not disagreeing at all. I just think that we need to be careful about the conclusions. That's all.
100%, and I actually completely, and I think the way you just said it, I would agree more with the way you said it than if I said it in ways that led you to think differently. And then just the one thing I point out though is that we do this all the time in math, though, right? Exactly this kind of like this bait and switch thing, right? You know, like as Jane pointed out, fractions, negative numbers. We're doing this all the time, and math is really counterintuitive. It's weird. We set things up one way and we say, but what if it's not? And then we have to kind of relearn stuff all over again. So I would argue this is.
Yeah, it's really cool that we can identify that in these little kids and then see how they adjust and how they change. Yeah, so it's really fascinating. You know, your results and Jane's results are just amazing. I'm really impressed. I actually have a different question actually for Stephan. I'll just jump in and ask it here. It's very interesting to me. I read your paper already that you were talking about, but it was the way you presented it was very clear. And I guess the interesting thing to me is you're looking at the correlation between the reverse distance effect and arithmetic performance. But in all these studies with kids, including Sabrina's that she just talked about, it's not the distance effect, the reverse distance effect that's being correlated with performance. It's overall performance on the order judgment task, right? And people seem to be not very careful about when they're talking about one versus the other. And if I remember, I think back to some of Daniel's work with Holloway and so on, the correlation between the canonical distance effect and arithmetic can sometimes go the wrong way too. So I guess do you have a comment about that? And do you think that the relationships we're looking for here are different kinds of relationships if you look at overall performance versus the distance effect performance?
So yes, absolutely. So I think when we look at overall performance and specific effects, we actually do look at different kind of things, because overall performance obviously involves a variety of different cognitive abilities that have to be in place in order that we can perform those tasks. More specific effects obviously aim to nail that down to really specific cognitive abilities that might actually drive some of the associations. So yes, I definitely would say that we look at different things when we look at overall performance. Unless you have any other overall performance control tasks that you can use in order to maybe make sort of a differentiation of that. But I think in terms of the distance effect and looking for individual differences, it has become, in general, I think a little bit of a reliability issue to some extent as well, right? So I mean, overall, there seems to be sort of a small consistent relationship with the canonical distance effect and arithmetic abilities. But in terms of using the distance effect for making like really individual diagnostic judgments, for example, I think it's not really well suited. And there are actually a couple of papers coming out that when using like really those specific effects, we don't really have a good hand on it, identifying individual differences with these effects. So I definitely agree that it's sort of an iffy issue using those very specific effects and to look at the very specific associations between the effects and arithmetic and other abilities. That is for sure. And maybe some of the inconsistencies are, as in the number comparison task, maybe due to different setups of the studies, obviously, and maybe some of the differences in our case in the ordinal verification task might be really related to just different concepts that are used to solve the task. And I think that also fits very nicely within the broader scheme of today's symposium, that it's not really straightforward what people are doing actually in the ordinal verification task, and that even trickles down to very specific effects and has an impact on that relationship as well. So I hope that roughly answers your questions.
Yeah, no, we all have the same concerns, I think, about that. And I just think that it's really important that people are clear when they talk about the relationship between the order judgment task and performance. It's very strong, as we know from Lyons and Bayesian 2011. There's a big honking correlation. But then if you start getting into these little picky effects, it's not the same thing anymore. And I think developmentally, we are looking at overall performance often, right, for those relationships, but then it switches. So no one's too careful, I think, when they're talking about it sometimes.
Absolutely, I agree. So in the paper that we wrote about the distance effect, I really specifically look at those papers who have used the distance effect in order basically to overall judge, also in terms of the numerical order task, whether there is sort of a consistent evidence of that association. And it seems to be more inconsistent, at least in the ordinal task than in the cardinal task. And I think some of the reason why that is the case might be this qualitative issue. And that also fits very nicely, I think, with the broader issue of the non-adjacent items, because the correlation is a negative one, right? So the smaller the reverse distance effect is, so the less actually difference between adjacent item trials and non-adjacent item trials, the better the arithmetic performance is, right? So that actually also shows that maybe this leveling out in terms of having difficulties in the non-adjacent effect is actually more important than actually looking at the inter-item distance one trials, and maybe this is also sort of driving that effect in the reverse distance effect.
Just want to make a quick point that actually I believe the first paper to show a relationship between ordinal processing and math achievement was Lefebvre and colleagues, 1986. So just I have a really quick question, actually, Stephan, regarding what you just said. I think that's super interesting, and it makes me kind of think. So for the longest time, we would look at the canonical distance effect, and we would talk about it as, say, precision of representation and that sort of thing, and various work, including some of our own, has sort of pushed back on that a little bit. And that's the sort of the difference between, far distance and close distance, and, yada, yada, and all that. But when it comes to the reverse distance effects, right, as you're sort of saying, as the difference between the 1, 2, 3 trials and the 2, 4, 6 trials, as that gets less and less, participants are getting better at math, or that's predicting that they're better at math. So I would argue, first of all, like the whole representational precision thing is unlikely to be relevant there. And so that really sort of makes us have to think differently about like what the heck that might mean. So what is that implication? And I was just wondering if you had any thoughts on that.
Yeah, well, very, very difficult question, right? So I think what our data show is just that it obviously is that maybe many different cognitive mechanisms might contribute actually to the reverse distance effect, and that people use maybe different strategies in order to make that decision, and that difference might be also obviously a meaningful one in terms of investigating associations with arithmetic. But I think my best guess at the moment is actually quite in line in what you have shown as well, right? So that maybe a reduction between distance 1 and distance 2 trials sort of is driving the association with arithmetic, at least in those individuals who show like the canonical distance effect. I'm a little bit unsure about what is happening in those individuals who show sort of a canonical distance effect in the numerical order condition, right? Like the reverse actually of the reverse distance effect. And maybe they use like completely different strategies at all, like more comparison strategies or a combination of a variety of different strategies in order to solve the task. So I think that actually variability in the canonical distance effect might be really a factor of different strategies and different combination of strategies, not just like the cognitive aspect that you were talking about, but maybe also additional cognitive aspects that individuals use, maybe also to overcome certain difficulties they have to make that decision. But exactly, so Jean Lefebvre is posting, I think, that paper that has looked, I think, in terms of questionnaires, what kind of different compositions might be used in order to do an ordinal task. And I think that is really an interesting topic to pursue in order to investigate that relationship a little bit more closely. Yeah, was maybe a little bit of an unspecific answer, but trying to wrap my mind around that question as well. So
Okay, well, I think since we've gone, 20 minutes over, we should probably call it a day. I'm sorry we didn't have more time for a lengthier discussion, but I'm sure anybody could follow up with any of us via email if you have any other questions, and I'm sure we'd be happy to answer. So thanks so much for joining, and enjoy the rest of your day.
Thanks, Jane.
thank you. Thanks, Jane, for
Bye.
organizing the symposium. Bye-bye.
You're welcome. Bye.
Thanks a lot.
No problem. Bye.